Now we're going to look at pressure and flow. So the key objectives for this session, I want you all to be able to, at the end of this part of the session, to be able to recognise the different units of measurement used to measure pressure and flow. Calculate the pressure at an outlet in bar and in pascals, and calculate the pressure at the base of a cistern. I also want you guys to be able to describe the relationship between pipework, fittings and flow. In this session we're going to look at the effect that pressure and flow rates in a plumbing system. We will look at the units of measurement for these and look at some of the calculations you might need to carry out. So pressure is force spread over area, and this SI measurement, System International measurement, scientific measurement of pressure is pascals. This SI measurement for force is actually newtons. I've muffed up there, sorry guys. So this SI measurement for pressure is pascals, and 1 pascal is equivalent to 1 newton of force spread over 1 metre squared of area. So 1 pascal is equal to 1 newtons per metre squared. Okay. You'll often hear people talk about pressure in bar. And that's the general kind of term that we're going to use in plumbing. But it's worth knowing that there's 100,000 pascals in 1 bar of pressure. You might also hear the term head of pressure used as well, and we're going to look at what we mean by head of pressure now. Okay, 1 metre's head of pressure, a 1 metre high column of water, would give you roughly just under, a tiny bit under 0.1 bar of pressure. Okay, so therefore 10 meters head of pressure is equal to roughly just a tiny bit under, like I say, of 1 bar. But to all intents and purposes, this is what we need to know for practical purposes. Each meter's head of pressure is equal to 0.1 of a bar. We will talk about how to do a little bit more of a specific calculation, because it comes up in the test, but in real terms, this is the thing that's worth knowing. Okay, 1 meter's head of pressure is equal to 0.1 bar of pressure. Just worth noting, the pressure is relative only to the height between the water level in the cistern and the outlet. The length of the pipe is irrelevant. This pipe could go left, right, up and down and be 20 metres long, but if there's 10 metres between the water level and the outlet, then the pressure will be 1 bar. Okay. And actually you can sort of see from this picture here, you can kind of see how pressure, the height of the water affects the pressure. You can see this big cylinder, this big tank full of water with 3 different sort of connections onto it. There's less weight of water above this one, there's a little bit more weight of water above this one, and there's a lot more weight of water above this one. So all of that water kind of pushing down pushes that water out the way, and you can see that this one shoots out a lot further because the pressure behind it is more. There's more of a sort of weight of water, more force pushing the water out of this one than there is this one and this one. Okay. The relationship is unaffected by the amount of water, just the height above the outlet. So say for example, we've got 2 examples here, both 15mm pipes, the bib taps connected on there. One with a massive giant cistern with 4 metres in height between the water level and the outlet, and one with a tiny little cistern up here with 8 metres between the water level and the outlet. And actually this one here with the 8 metres head of pressure would have 0.8 of a bar of pressure at the outlet, whereas this one would have 0.4 of a bar of pressure, because it's only relevant. The only thing that's relevant is the height. Okay. So yeah, like I said earlier, the 0.1 of a bar is only a rough guide. You can work out the exact intensity of pressure by multiplying the height in meters by acceleration due to gravity, and acceleration due to gravity is 9.81 meters per second. And this gives you an answer in kilopascals. So we'll take this example here with our 8 meters of head of pressure. We'll take our height in meters, times it by acceleration due to gravity, so 8 times 9.81 gives us an answer of 78.48 kilopascals. Bearing in mind it's kilopascals, okay, which means 1,000 pascals, so that's 78,000, sorry, sorry, 7,840 pascals. No, it should be 78,000 of 78,000 and 40, 78,480 pascals. Yeah, I've written that wrong again. Okay, so it should be 78,480 pascals. I need to adapt this PowerPoint. So, total pressure on a set area. You might be asked to calculate the pressure over a set area. They normally ask you what's the pressure on the base of this cistern, for example. Okay, and to calculate this, you need to work out what the pressure is, and that's going to be the pressure spread over. When you work that out, that would work out the pressure if it was spread over a meter squared, and then you can sort of work out the total pressure on the base of the cistern then by multiplying the length and the width, and that would then sort of tell you the total pressure over the area. So for example here, we've got 3 meters in height, so we do that 3 times 9.81 gives us 29.43 kilopascals, or 29,430 pascals. And then we multiply that by the total area of the base, which is, in this case, it's 1 meter by 1.5 meters, gives us an area of 1.5 meters squared. So the total force applied to the base, or the pressure over the entirety of the base, is going to be 44.15 kilonewtons. So when water is delivered into the property, just like with our stored water, when the mains is delivered into the property, actually the higher it gets, the less force it has behind it, the lower the pressure. So point D is going to have the least pressure moving back towards point C, point B, and then point A with the greatest pressure, the highest pressure, because that's right where the water is getting pushed into the property. And we can change the pressure actually by heating the water sometimes, because as you heat the water, causes the water to expand, it will increase the pressure, and we need to be very, very careful with this, particularly when designing unvented systems, because if that water expands too much, it can cause pipes to rupture, can cause damage to components, and could potentially cause some serious harm to customers. So that's part of the reason why we need to take a lot of precautions with hot water and heating systems, particularly unvented hot water and heating systems, to make sure that we prevent that from happening. And partly what we do, we put in expansion vessels, we put in pressure reducing valves, pressure relief valves, etc., to keep the system safe, keep the people safe. Another way of increasing the pressure could be in fitting a pump, and if you fitted a pump, it would also, generally speaking, increase the velocity, the speed of the water flowing through the pipe. But interestingly, you can also increase the speed of the water by reducing the pipe diameter. And a good way to think about it is if you take a hose, you get that hose that's sort of spraying out just a little bit, you put your finger half over the end of the hose, suddenly that water is shooting out really, really fast. You've not increased the flow rate, and actually what you actually do is you also decrease the pressure, interestingly. So you cover your finger half over the end of it, the water shoots out much more quickly, the velocity is increased, but the pressure and the flow are actually both decreased. And there's an interesting relationship between pressure and flow and pipe diameter. So yeah, if you reduce the pipe size, you reduce the pressure, you reduce the flow, but you would increase the velocity. Velocity can be measured in, well, it's normally measured in meters per second. And acceleration is measured in meters per second squared. So flow rates, flow rate is the amount of material that passes a point at any one time. There's lots of different ways it can be measured. It can be measured in litres per second, kilograms per second, or meters cubed per second. And when we measure it in plumbing, we normally measure it in sort of actually litres per minute. But you can change that to litres per second by dividing the answer by 60. And you can see a weir cup here, a flow, some people call it a flow cup, which can be used to sort of measure the amount of water flowing from a tap in litres per minute, which again we could divide by 60 to change it to litres per second. Flow rate can be affected by lots of different things. Pipe pressure, like we've talked about. Also, the diameter of the pipe size, the pipe material. Some materials have got a rougher internal bore. For example, steel's got a rougher internal bore, which will affect the flow rate through it. So steel will generally give a poorer flow rate and not as good a flow rate as copper or plastic. But one of the biggest things that affects flow is the type and the number of fittings, particularly bends, on the system. As I've mentioned already, the rate of flow through a pipe is affected by the frictional resistance of the pipe, and because steel has got a rough internal bore, it will affect the flow rate. The example shown here, you've got 10 meters length of 28 mil copper or plastic, would give a flow rate of roughly 22 litres per minute, depending on the pressure. Whereas that same length and same size of steel pipe with a rougher internal bore would only give a flow rate of 18 litres per minute, because of the rough internal surface that slows down the flow through the water. But the thing that has the biggest effect is the type of fittings. Elbows, which are fittings that we might solder on or use as compression fittings, would give about 50% more frictional resistance than fabricated bends and bends that we'd make with a bending machine. That's because it's easier for the water to flow around that smooth bend from a bending machine than the sort of sharp bend from a fitting. So if you replace your fittings with formed bends, you would significantly improve the flow rate in the system. Okay, now it is time for your task.